After just 5 minutes under this condition, you become dizzy and confused. Your heart rate dramatically increases, and your brain cells begin to die. This is called hypoxia, the lack of oxygen to our body. And while it's potentially fatal to our normal cells, it causes cancer cells to become more aggressive, resistant to chemotherapy, and more likely to metastasize to other areas of our body. These big, nasty balls of cancer cells grow so fast and become so densely packed that not only does oxygen not penetrate, neither do our best chemotherapy drugs. So what if, instead of trying to attack the outside of the tumor, what if we try to attack the inside, where the most hypoxic and aggressive cells are? To do this, we designed a drug delivery vehicle called a nanoparticle that is 10,000 times smaller than a pinhead, containing two critical components. The first is an azobenzene linker, which is a fancy chemical group that holds our nanoparticle together. This linker is sensitive to hypoxia and breaks under low oxygen concentrations, keeping our toxic chemotherapy drugs inside until they reach the tumor, lowering the chances of medication side effects. Unfortunately, traveling through our blood vessels to find a small tumor is like a road trip without a map, because if you stretched out our entire vascular system, it would reach around the whole world, twice. For this, we designed a small peptide made of 9 amino acids that works like a GPS system for our nanoparticle vehicle. Turn left at Hart Road, take the second right onto Kidney Drive, on and on until you reach the tumor. Once our nanoparticles reach the destination, the small peptide knocks on the front door of the cancer cells. The cells then either let the nanoparticles inside or send them further down the road, deeper and deeper into the tumor core. When our linker and peptide work together, our nanoparticle vehicle drives to the site of the tumor, steers itself to hypoxic areas deep inside, and then explodes, releasing the toxic chemotherapy, destroying the inner structure of the tumor, causing it to break apart, creating a massive surface area in which standard chemotherapy can now easily attack. This method has been proven in a mouse model of pancreatic cancer, and a partnership with an oncologic surgeon gives us insight on how to move our therapy from the bench to the bedside. With a continually increasing mortality rate, pancreatic cancer will soon be the second leading cause of all cancer deaths, something that we hope to change. Thank you.